This video shows how to use ECORCE. It's the first step to apply to understand the behavior of ECORCE. So as the first time, our goal now is to create a simple MOSFET. To begin, we need to create a new simulation in 2D dimension. There are three parts inside ECORCE. In this part, there are all the commands needed to create a device, apply stimuli, and execute calculation. This one is a workspace, and this is only to drive drawing parameters. Here, we are in beginner mode. When you will advance in the use of ECORCE, you will need to switch to advanced user, expert user, or experimental user. Every time you increase this, you will see additional functions appearing inside ECORCE. For now, we advise you to stay in beginner mode. We adjust the dimension of the device, 1 micrometer by 1 micrometer. Now I want to create the geometry. Clicking here, create a new node. It's blinking, this means it's selected. When clicking there, it creates a second node and a line between the two nodes. And following the shape of the silicon of my device, I create the full edge. In case of mistake, ECORCE is compatible with undo redo. To do this, select Edit, and here you have undo and redo, and the shortcut associate. So, this will be silicon, and I reserve place for drain contact, oxide, and source contact. Now to create the oxide, I unselect this node by clicking on it. And now I create the oxide here. As a general rule, all the functions in ECORCE must be followed from left to right and top to bottom. So now I have finished the creation of shape. We can now create contacts. Here will be the drain, the gate, the source contact, and the substrate contact. ECORCE is also designed to have all inside material. I do not need this function here, but I have to say, here I have this material, and here another material. To do this, I click on surface. So here we will have a material, and here another material. It's finished for the creation of the geometry. Now, in this second time, I will add to the geometry a physical model. I click on physics mode. I must define the equation needed, so the equation of Poisson is already selected. I select the transport of electron and the transport of all. Now I must define the name of my contact. This one will be the drain, this one the gate, the source, and here we have the substrate. I must also define the materials themselves. So I click on material. This one is not silicon as selected by default. We must select oxide. The parameters for the oxide have been automatically restored from the library that is inside ECORCE. And this one is already silicon. It's also useful to give names that are significant to material. So this one is silicon, and this one is insulator. Last step for the creation of the physical model, we must define the doping. To do this, we click on Function. It's a NMOSFET. This means that the substrate is acceptor type. I create a new function, value 10 to the 16, from 0 to 1 for x, and from 0 to 0.5 for y. But because there is a common point between silicon and oxide, we have also some doping that will be inside the gate. To avoid this, I precise that only silicon will receive this doping function. So I click on silicon. Now I must define the n+ area between drain and source. So I create a new function for the donor type doping. I click on donor, then new function, 10 to the 18, from 0 to 0.3 for X, and from 0.4 to 0.5 for Y. Here again, at that point, doping will be applied inside the oxide, so I precise only on silicon. And I create the last one, 10 to the 18, from 0.7 to 1 for X, and from 0.4 to 0.5 for Y. At this point, some doping will be applied to the oxide. Let's say I forget to apply it only on silicon. We will see the error message that will be generated by ECORCE. The physical model is now finished. Now I must define the biases applied. So I click on Param Stimuli. For now we do simple modeling in stationary mode. I go to Stimuli, create a new bias. It automatically applied to the drain. Let's apply 0.1 volt. I create a new one. On the gate I want a ramp of bias from 0 to 5 volt. For the gate you can see here the bias as a function of step number. On the source we apply 0 volt and on the substrate 0 volt. Now we can execute the calculation. No need to define any mesh, thanks to the dynamic mesh creator of ECORCE. It will be done automatically and corrected at each step of the modeling. So I click on Process, Execute. I must save my modeling, so the first name is for the device, NMOS, and the second name is because we can apply several biases on the same device, and also irradiation and any stimuli. So for now, we are creating the ID of VGS characteristic. Click OK, and now I have a warning there. Remember, we didn't limit this doping to only silicon. So I go back to the doping, and here I say it's only inside silicon. I click Process, and I execute again. I ask for 4 processors to have faster calculation time. I execute. You can see here it's running. You can see here the step number increasing. The simulation is finished. And now we can see here, this is our original device, and the third dimension displays the potential here. So here we applied 0.1 volt. We can see the value displayed under the mouse here. So here we have plus 0.1 volt plus the Fermi level of the device to take into account the electric field generated by the materials. Of course, the difference of potential between the drain and the source is 0.1 volt. Here we have 0 volt plus the Fermi level, and at the gate we have exactly the same thing but for the oxide. Here you can see the mesh generated automatically by ECORCE, so of course it takes into account the variant of carrier potential and so on to define the position of each node. And of course I have several steps. By increasing the step number, you increase the bias on the gate. I go back to the first step. What is also interesting is to see the creation of the channel. So I select now the electron density as the log scale, and I can also create an animation to see the change as a function of bias. So I select here animation, I reduce the time between each image, and I press start animation. Now you can see the creation of the channel. So you have many possibilities to analyze your result. I stop the animation. Now what is also interesting is to see the ID of VGS characteristic. So the volume result we are for on is made to display the value of potential and so on for one step in the full device. Now if I want to see the current for the drain as a function of gate bias, I switch to global result. In global result, we need to define what is along the x-axis. So I want to see the potential applied to the gate from 0 to 5 volt. And from the y-axis, I want to see the total current on the drain. You can see the characteristic here. Of course, the threshold voltage is around here. We can add a more precise value using function. So this function here calculates the intersection of the higher derivative with the x-axis. And we get here the threshold voltage 2.3 volt. I can also log for y-axis to see the leakage current from VGS 0 volt. This is the end of this tutorial. In the next video we will show you how to apply radiation and higher level function of ECORCE.